Critical Chain Project Management, or Ccpm, is a tool for managing multiple projects. We have used it successfully in managing overhaul of aircraft and the overhaul of jet engines. An example of a project is developing a new product or creating a new software release. Projects have multiple tasks and involve multiple people and multiple resources, such as equipment. And in most organizations, we must simultaneously manage multiple projects, all competing for the same people's time and for the same resources. In reality, projects are much more complex than the one shown here, and in reality, they all are different. But for our purposes, it's okay to pretend that they all look like this. We can still illustrate the key learning concepts under that assumption. In project management, we often find ourselves in a vicious cycle. Flow times are long and unpredictable. So at the beginning of the project, there's lots of uncertainty in the specifications of the product or the software. There's lots of uncertainty in when the people doing the different tasks will be needed, and there's uncertainty about when resources such as test equipment will be needed. This makes planning uncertain, and it makes it more unlikely that the specifications will stay the same, that the people and equipment will be available when they're needed. And changing specifications and unavailability of parts and equipment makes the flow times even more long and unpredictable. Here are the 4 key points that you should learn from this video. Since projects take so long, we induct them as early as possible. We also do that to keep people busy. In other words, we start the project as soon as the person who does the first task in that project becomes available. Ccpm says do not do that. Second, since there are so many projects in the system, individuals tend to multitask or to work a little bit on one task and then a little bit on another one. Often this is dictated by what equipment might be available at a given time. Ccpm says do not multitask. Do not begin working on a task until you have everything you need to work it to completion. Third, when we estimate the time that a task in a project will take, we inflate the estimate just to be safe. Ccpm says do not do that, quote, very aggressive task times. And finally, when someone is deciding what tasks to do next, Ccpm gives us a very specific criterion called the buffer burn rate, which we will define later, that allows us to decide which task to do next. This rule is designed to make project completion times shorter, but even more important, to make them predictable. Let's first talk about when to start a new project. There's a rule called Little's Law that simply acknowledges that the more projects or more work in progress, WIP, that you put into the system, the longer your flow times will be. Thus, when you're pushing more work into the system, starting projects as soon as possible, you are literally driving up the amount of time they will spend in the system. If you are turning out a project, let's say about once every 10 weeks, and you have 7 projects in the system, that's 70 weeks of projects in WIP, and you have an average flow time of 70 weeks. Here's the reasoning behind Little's Law. In the previous slide, you have 7 projects. Suppose on average you complete a project every 10 weeks. When a new project comes in, there are on average 7 projects in the system. The new project is number 7. If they leave one every 10 weeks, first in, first out, it would be 70 weeks before number 7 would leave. The arithmetic of Little's Law is that we divide the WIP by the production rate. In this case, the WIP is 7 projects, and the production rate is 1/10 of a project per week. An even more important thing that Little's Law does not tell you, the variation of flow time also goes up as WIP increases. The flow time will not be exactly 70 weeks, it will be 70 weeks on average. A particular project might take much longer or even much less. That unpredictability is what makes scheduling resources and support so difficult. If we look at our resources, we can see that pushing more projects into the system doesn't necessarily increase the rate at which projects exit the system. The rate at which projects exit the system we will refer to as throughput. The throughput is determined by the resource that is the constraint. In this case, the constraint is resource C. It can complete a project every 10 weeks because under our assumption, each project requires 10 weeks of resource C. We want to start new projects frequently enough to ensure that C always has work to do. That would be about one every 10 weeks. But inducting more projects than one every 10 weeks just to keep A busy, for example, will not increase throughput. It will only increase WIP as more projects pile up in the system. There is a technique called drum buffer rope that says, let's let the constraint be the drum beat. Each time the constraint completes a project, that's a signal to induct a new one. We always keep enough projects in the system to ensure that the constraint is busy. In class, we will go into the details of how to do this. So let's see what happens if we control the rate of induction to match the rate at which projects are being completed at the constraint and hold WIP constant at 4. In this example, 4 pieces of work corresponds to 40 weeks of work. So by containing WIP at 4, we have reduced our flow time from 70 weeks to 40 weeks. Incidentally, Delta Airlines in their engine shop found that this single thing, controlling inductions, gave an immediate boost in productivity or the production rate. You waste a lot of time when you're dealing with all that extra WIP in the system. One of those wastes is multitasking. What you want to do is to put rules in place that say you cannot begin work on a task in a project until you have everything you need to complete it, and you will work on that one task until it is completed. The picture on top shows what happens when you work 4 jobs without multitasking. Each job in this example takes 4 weeks, so you complete the first after week 4, the second at the end of week 8, the third at the end of week 12, and the fourth at the end of week 16. The bottom shows what would happen if we were to multitask. For example, work a week on one job and then switch to another and so forth. We finally get a task completed, task A, at the end of week 13, and then the others follow that. But the most important thing is not shown in this drawing. That is the time that you waste switching between tasks. Let me repeat that. Changing between tasks will cost time. And in addition, it will cause more mistakes and more defects. Let's talk about how we tend to estimate task times. This drawing shows what happens. We have a task. We don't know how long it will take. It could range from 2 weeks to 8 weeks or more. But let's assume that half the time the task could be completed in 4 weeks. What will we give as an estimated task time? Common practice would be to allocate 8 weeks, or kind of the worst case, to complete the task. That seems like the prudent thing to do. Allow enough slack or buffer to give a high probability of completing the task within the allocated time. When we allocate a task time of 8 weeks, even though the task could possibly have been completed in 2 or 3 or 4 or 5 or 6, whatever weeks, the 8 becomes a self-fulfilling prophecy. You're students and you know that. If a professor gives a 4-hour assignment that is due in 2 weeks, it will get done in 2 weeks. For the reasons shown here, people do not tend to complete tasks early. They behave in ways to complete the task in the time allocated. And if something goes wrong, it may take even longer. So by being prudent, by building some slack into the task time, you have ensured that a task that had a 50% chance of being completed in 4 weeks will take at least 8 weeks. To make things simple, let's suppose that all of our projects look like the one shown here. We have built a buffer into each task, and even if nothing goes wrong, this project will take 34 weeks to complete because we have allocated all of that extra time to each task. If we take a big picture view of all of the projects, what we really want is to be less uncertain about the completion times of the projects. We're not really particularly interested in the completion times of individual tasks. We don't want each task to be completed by a certain milestone. We want them to be completed as quickly as possible. Ccpm says set a very aggressive task time. In our example, let's remove from each task the 50% of the time that we have called buffer. Before, the critical path was 34 weeks, and now it is 17 weeks. Second, let's give some of that buffer time that we took from the task to the project. But we won't need all of it unless all of the tasks took their most pessimistic estimate. So let's give the project half of the 17 weeks of buffer that we took from the task. I've rounded to 8 weeks. I've also cut the times of the non-critical task in half and inserted a feeder buffer at the end of those tasks. Third, we no longer view the task completion times as milestone. We have intentionally set very aggressive times that we will meet or beat half the time, and we will fail to meet the other half of the time. These task completion times should be viewed as handoffs in a relay. Complete the task as quickly as possible and turn it over to the next step. As the task may take more than the time allocated, that is what the buffer associated with the project is for, is to absorb that. In our new plan, we have reduced the project completion time from 34 days down to 25 days. That will work only if the overrun on the task on the critical path do not exceed the amount of buffer that we have planned for the project. In other words, when a task takes more time than allocated, the purpose of the project buffer is to absorb that variation. And we monitor the project to make sure that that is what indeed is happening. In the earlier diagram, we have reduced the project completion time from 34 days to 25 days. That will work only if the overrun on the task on the critical path do not exceed the amount of buffer that we have assigned the project. To monitor the project and prevent that from happening, we use something called the buffer burn rate. To simplify things, let's suppose that the critical path of a project contains these 4 tasks, each with a task time of 2 weeks. When a task exceeds its aggressive task time of 2 weeks, it consumes some of the project buffer. For example, if a task takes 3 days rather than the planned 2 days, a day of project buffer is consumed. To monitor the progression of the project, we compare the fraction of the project buffer that has been consumed to the fraction of the project that has been completed, and we call that the project or the buffer burn rate. For example, suppose that as in the picture, the first 2 tasks having a total time of 4 weeks have been completed, and let's suppose it's now day 5. That means we have used 1 day of the 4-week project buffer. So we have used 1/4 of the project buffer. We are halfway through the project. Our buffer burn rate is 1/4 of the buffer consumed over 1/2 of the project completed. So the burn rate is 1/2. We are in the green zone. If it's instead week 6 when we complete half of the project, we have consumed 2 weeks or half of the buffer and have completed half of the project. Our buffer burn rate is 1/2 over 1/2 or 1. We are in the yellow zone. If instead it is week 7 when we complete the first half of the project or the first 2 tasks, We have consumed 3 weeks of the buffer and completed half of the project. Our buffer burn rate is 3/4 of the buffer consumed over 1/2 of the project completed, or 1.5, and we are in the red zone. Note that at the end of the project, if it takes exactly 12 weeks, we have used all of the allocated buffer, and our buffer burn rate would be 1. That is our goal, to hit that and be predictable. Our goal is not to complete some projects early and some late, but consistently do what we said we were going to do. This shows how we use the buffer burn rate to set priorities among tasks from different projects that are competing for the same capacity. There are 4 tasks here. Let's first look at task 1. It is associated with a project that is about 3/4 completed, and in the past we would have probably worked task 4 first in order to get that job out. And task 1 probably has been in the queue the longest, so first in, first out logic would dictate that it be next. But the project that task 1 is associated with is 3/4 completed and has used only 1/4 of its buffer. It is clearly in the green zone. And our goal is not to complete some task early and some late, so that on average we're looking good. Our goal is to be predictable in completing every project and its allocated completion time. Let's look at task 4. Its project is only 1/4 complete and has already used 3/4 of the buffer. We need to act by giving task 4 first priority in the queue and minimize the chance of using up more of its buffer. If we do that for the other task associated with the project, it will move back toward the yellow zone, and then this will drive the project toward on-time completion. The priorities here are first task 4, then 2, then 3, then 1. This moves each project back toward the yellow zone and toward an on-time completion. I've given a big picture view here and have left out a lot of the details. We didn't have to determine which tasks are critical, that is, determine which task would automatically delay the project. Our example had only a few tasks, so that most of them were critical, and we didn't have to talk about how to put a feeder buffer in for the non-critical task. But I've attempted to illustrate how to make the project flow be shorter and more predictable, and that makes life much easier when we're trying to schedule resources and set specifications for projects. Here is what I would want you to remember about this presentation. The very foundations of critical chain project management. Controlling induction to keep WIP and flow time shorter. Avoid multitasking by not starting a task until you have everything you need to complete it. Schedule tasks aggressively and build the needed buffer into the project. And use the buffer burn rate to prioritize work.